today's session. And today's speaker is Qingsong Wang with a survey of some results devoted to asymptotic behavior of the intersection local times. Please, Qingsong.
Okay, thank you very much for introduction. Okay, I will share my screen now. Okay, I think you can see it, right?
We can see, okay, now we can see it, yeah.
Okay, thank you very much. Today my talk is about the asymptotic results for Brownian motion intersection local times. So to begin with it, I will introduce some basic knowledge and like definition for it. So let's begin with it. First, the theory of local times was found by Levy in 1940. That he proved that for the function of the following kind, which defined by the Lebesgue-Meyer, which about the time which is spent of one-dimensional, of course, here considered for one-dimensional, that is a one-dimensional Brownian motion spent under the level x. And he proved that this function is almost surely differentiable with respect to x. And from this, we can give the definition of the occupation measures. Here's that we still consider that in one-dimensional case for R1, that an R1 valued stochastic process that time is during 0 to t, we can define occupation measure on the Borel set on R such that the measure about the Borel set D and the time t, which is defined as the Lebesgue measure of the which contains the time that the Brownian motion spent in the set D. This is a definition for the occupation measure. And the next Total proved that in 1958, he proved that the occupation measure still considered one-dimensional Brownian motion, that this measure has a density, and proves that the density is continuous with respect to the both parameter x and t. And in this time, people call this density is the local time Brownian motion. And based on this result in 1965, Ito and Markin proved that this one-dimensional Brownian motion local time has a representation. Here, the local time can be represented as the limit of the somehow like the limit differentiable of the occupation measure under the case that the left end of the interval, which is close to the left part. And so, since we introduced this previous knowledge, we can give the definition of the local times. Still considered the one-dimensional stochastic process that it's defined on 0 to t. We can, of course, like before, we can define its occupation measure. Still is mu dt. Consider the d is the Borel subset in R1. If of sure this measure has a density, like I said before, that then we can see this mu is called the local time of the process x. So this is about the local times. And next, I will introduce something about the intersection local times. The intersection local time is motivated by like for from the physics, because some physicists consider about the geometry of the shape of the polymer, and maybe somebody know about that the polymer, which often is described by like some random process, such as like a burning motion or something. So the geometry of a polymer is decided by the intensity that the random path intersect itself. So it's reasonable to consider the intersection of types. And for intersection of times, usually maybe one can consider like two kind of it. For first one, somebody may call it like the multiple self-intersection local times. Some we can consider the still we consider the for Bernoulli motion, and in one-dimensional case, and we give a natural number which is a p. That is a p multiple self-intersection local time, which can be defined as follows. We consider the time set is a that is 0 to t with power p. And we define this random variable, or even we can say it's a random measure, which is equal to the integral of here the L is a local time of W at x that with p's power even, and can be defined as such a kind of integral of the delta function. And like I said, it is called the p multiple self-intersection local time, and it's used to counting the number of the self-intersections over the time set A of Bernoulli motion. So this is about the first kind of self-intersection local times. Next, some may call it the mutual intersection local times. Here we consider the is P's independent one-dimensional Bernoulli motion. But still we can consider the time set is 0t with p power. Here we can define the random measure omega a, which is given in the following kind, which is maybe somehow similar to it, but to the previous one. But here we consider, maybe I can draw, please. Maybe I can try to draw something to say it. Okay. Right, draw another kind. Here it means what if here's like several, like here is a piece independent Bernoulli motion. It considers such a things that here consider like p is equal to 3, that this is a 3 independent Bernoulli motion, which intersect in this point, maybe I denote that as x. So this is what this definition means. Please replace this. So this is the definition for the mutual intersection local times. So after give these definitions, please allow me to, sorry, I don't know how to quit. Please allow me to introduce some known result for the mutual intersection local times. So here consider the independent, but here's consider for d-dimensional, that for d-dimensional independent Bernoulli motion, we may ask the well, when they will intersect. And this problem was proved by these three guys in 1950. And here's a really famous theorem. It says that if we denote the set S, which is intersect about the point that this independent Brownian motion intersect, just like I draw a picture before. If we denote this intersect point as a set of S, uh, then if it contains a point other than zero, under the condition that here's this inequalities. Sorry. Because here we don't consider about the point zero, because here what to consider is this Brownian motion start from the point zero. Under this inequality condition, of course, if as whether this Brownian motion will set is connected to the dimension, and also about how many independent Brownian motion we considered. So it's natural. So here this result shows when the mutual intersection local time exists. And next, I will show a result related to the large deviation principle for the mixed intersection local times. Here, the mixed intersection local times is like the combination of the two previous about the self-intersection local time and the mutual intersection local times. So because it considers such a case that if here's a m independent Brownian motion, if they intersect together, but we will consider all of them intersect p times, like combination of previous this guy and this guy together. And here denote to be the LJP. And this theorem from Chen and Li in 2004, which gives the large deviation principle for this local time. And here like this theorem says, the constant is given by of course it can be expressed by a formula, but I didn't show it here because the formula may be a little long, and it will need some other like basic knowledge about something else. But I maybe don't need to show it here before. If someone is interested, maybe can check this paper for more detailed information. So next, I'm trying to go into show the idea of this proof of this theorem. The idea of the proof is firstly, it's based on the famous theorem, like I showed here. This theorem says that if the logarithm of this part, the logarithm Laplace transform, if under the case that the lambda is tend to infinity, then it will convergence to something. Then, if we consider the large deviation for this local time, here mathematic this rate function is just exactly this, the exponential of this constant. So that's this theorem. What this theorem tell us? So of course, if we want to prove the previous large division principle, we just need to investigate if this equality holds. And if we want to prove this equality, first we'll begin with, I'm sorry, here's a mistake that we will begin with the left part, but not the right part. By some calculation, one can get that the left part is equal to such a form that the supreme of such a difference, where this big F denotes a set of absolutely continuous function G, and satisfying that the twice integrate is equal to 1, and the derivative of its twice integrate is less than infinity, to make sure this exists. And if we can get this equality holds, then we will go to deal with this guy. And to deal with this guy, we need some other knowledges. Please allow me to do that. We will use such a result which is based on the Feynman-Cat formula. Here it gives us that this logarithm Laplace transform of such about a function of Bernoulli motion, which can be expressed as a following form. Here, this G is just like exactly same as here. We'll use this result. Well, how we can use it? The idea is that we will prove that this. Maybe I can draw something here. If we denote this to be, sorry. If we denote this to be the formula 1, then we will try to prove that the 1 is less or equal than this guy. And by this result, of course, 1 will less or equal than this. If maybe we denote here to be 2. And then what left is just need to estimate this 2 to get a bound. What of something that this guy will less or equal, and we'll find a bound. And of course, we find for this for 1, and this is exactly what we want to get. This is for the lower bound. And so this is just the idea of the proof, but I don't show how detailedly it will need to do. So since here we mentioned the Feynman-Cat formula, I will say a little about what this formula is. The Feynman-Cat formula is says that if here's a unique solution to the PDE with the form of the following form, where this L, sorry, this guy means maybe I can call it. This guy is the infinitesimal generator of in our case is just the infinitesimal generator of Bernoulli motion. Of course, it's a Laplacian. And for this V is some potential function. If the solution to this PDE with the terminal condition that U big Tx is equal to such a function, then we can get a formula for this solution, which can be given by the conditional expectation of such a things. And where the x, if in the previous case, is just the Bernoulli motion W, and this is like the star. This small x is like the start point of the x. Then here's a exponential terms is some called the discount factor or the Feynman-Cat weight, which counts for the potential over the time interval from small t to the capital T. So this is the Feynman-Cat formula. And next, I will introduce something, some others work. Now here we try to investigate another measure, maybe a little different from before, that this L, which still like something is the intersections of P-independent and D-dimensional Bernoulli motion. Here even consider the cases D is greater or equal than 2. Sorry, here's some mistakes. For an open bounded set, that the LU is defined as such a integral of the steward function, and this measures like the projected intersection local times, and it says that it quants the meter intensity of multiple Bernoulli motion in the d-dimensional space. So have the and this is by someone maybe call it the symbolic formula, I remember. Okay, and since we have this like a definition or formula, this two guy investigate the large deviation principle of this probability, and also get the rate function. Here considered as the U belongs to RD is a bounded region, and it gives a result of course, it's a large deviation principle, where this P, of course, is some natural number, but this rho is a value which is defined by a variational problem, and it's related to Green's function, of course, in the region U. But maybe I didn't say what exactly these guys get and what it forms here, because I just will show the idea of the proof. If someone is interested about it, maybe can check this paper, and I will show the reference at the end of the talk. So next I will show the idea of this proof. First, just use the Tauber's theorem to translate the logarithm probability to be the integral moment of this form. Sorry. Of this form. And then he used a famous formula which called the Legauss moment formula to get the explicit expression of it, which is in it involves Green's function. And then what need to do is to investigate the expected explicit expression, and one will get the final result. Here here's the proof mentioned the Legauss moment formula, which is a very famous one. So I will introduce it. The Legauss moment formula, which says such a thing that for a natural number k, if we denote a set sk, which is a permutation, we use delta to show it, that is for the number 1 to k. And if we denote the start point x1 to xp for piece-independent Bernoulli motion w1 to wp, then the expectation of this of the local time with case integer has a following representation. And in fact, if to get it, of course, it needs some calculations. But one can imagine that if we take the previous uh, formula of Lu, like here, this guy, if one take it inside and write the expectation as an integral, and it will be something like the proof of this formula. And here, like I said before, here's G is the Green's function for Brownian motion, or it was defined as the integral of the transition probability, where I use PS to denote it, is the transition probability of Brownian motion. So this is Legauss moment formula. And okay, so the proof is just use this formula to rewrite the expectation and then to estimate for the Green's function to get the desired result. So this is like just the idea of the proof. And it's in fact divided like three parts. Like for first to solve the unboundedness, which can be handled through the truncation to control errors. And the integral domain can be partitioned into finite small intervals, and finally by some combinatorial tools to solve the problem. Finally, the asymptotic behavior can be derived by the leveraging large deviation principle. And of course, like I mentioned, it's related to variation, no problem. But I just like show the idea of the proof, but I don't show the detailed proof here. And also in the previous paper, it gave another result for the sig point. First, I will give the definition of what is a sig point. This is first, if we give explicitly a gauge function satisfies that the measure of a ball with center at x with radius r satisfies such an inequality, which is the sub of the limit sub is finite. Then we will call point x belongs to S, where the S is what I defined before. Maybe I will recall it what is. It's a intersection set. It's a little far. Yeah, exactly this set, the intersection set. Okay, if the x belongs to the intersection set, we'll call it a sig point. If this lim sub is greater than 0, then we call x is the sig point. Then this paper show these two guys in the paper in 2002 shows the following result that still considers the intersection local time, but for two independent Brownian motion in R3. Then he shows this equality, and this equality is just that he shows what the gauge function is in fact in this form. Maybe I can emphasize it. Yeah, for the first part of the theorem is to show what the function is. And then he discussed the Hausdorff dimension of the set of sig point, and which exactly shows that how many the sig point is. Of course, okay, and this rho star maybe is get by the previous result. the variational problem. Okay, and next I will also just try to give the idea of the proof. I didn't give the proof for this part, but I will discuss a little about the how to get the host of dimension for the set of sig point. The proof is divided into two parts because we say this is equality. So the idea is just to prove it less or equal than it and also greater equal than it. Then of course it will equal to it. So the proof is divided into two parts to get to prove it will be the upper bound and also the lower bound. The idea of the proof is that first to build a unite cube which can be a covering of the set R3 because the theorem is considering R3 to build such a cube covering of R3 but erase the point 0 because we consider the sig point belongs to the intersection set, but the intersection set didn't contain the original point. And also it's the start point of the Brunner motion. First, we will denote a sig point as before, as follows, just as follows. It's a set that satisfies such a equality, and to build a cube, which is equal to a b plus the interval with 3 power, and then with this cube, we defined a sig point in C, which is defined by this is the FA. Then what we need to prove is that to prove the hostile dimension of the intersect of HA intersect with the cube C, which is less or equal than the dimension of FA. And we can get the dimension of FA is exactly less or equal than the constant what we need. So this can give us the upper bound. Here's just like I said, we want to build a cube as a covering of R3, and then to prove this, it will be, and then by this equality we will get it. Then for the lower bound, it's by some other things. Here just simplifies the notation to define to denote the constant to be just 1 gamma, and try to investigate the probability of the dimension of the a sig point intersect with a ball with center to 0 with radius r, if it's greater or equal than this constant for r, which is exactly equal to the limit of such a probability. Of course, it's greater than 0, but we can get in fact this by the 0-1 law that this probability is in fact is equal to 1. So what it can tell us, it can give us that this probability equal to 1, that of course it's for this probability, or maybe I will write a little bit about it. Of course, this probability, maybe I denote as 1. Here the 1, of course, is greater or equal than the probability that the dimension of the HA, which is greater or equal than the gamma. Yeah, of course, it's true. And if we get this this probability is equal to 1, we'll get this probability also must be true, and this dimensional must greater equal than it. And so that's it. That's a proof of this. And next, I will introduce another work that is to establish for the occupation time for single Bernoulli motion, particularly through the Feynman-Cat formula and dv large deviations. To understand the property of intersection local time of multiple independent Bernoulli motion is very difficult. And this is because the different differential equation correspond to the intersection local time is nonlinear, and its lack of analytic tool to the Feynman-Cat formula like I gave before. So next I will show the result about the existence of extension moment for intersection local time, and also just show a theorem which is called the law of large mass. Before to show the result, I will give some basic knowledge before that the P independent Bernoulli motion here we consider that it's in a region which B is open and bounded, and just consider stopped at the where the Bernoulli motion is start inside the region B, and it will stop at the first exist time. Consider the local time, which defined as the following form. Yeah, this. Here this L is defined as before, but in this work it considered such a form of to consider the result for such forms. Where this inside this it's this inner product is defined as integral, where the L is defined as before. Maybe I will shortly recall it. Here, this is what L defined. And here inside this phi is a R non-negative function, which with compact spot. What this means is just like a spot of it is a compact subset of B with the following form. Then next I will introduce the basic definition of the function space. What this theorem considers is for this Sobolev space under the condition that B is bounded. It's considered as H01B. What this function space will give us is will make sure that on the boundary the function is equal 0. But under this case, if B is RD, which is not bounded, but this D1, the function space will make sure that the function, if tend to infinity, it will vanish. So that's what this functional space will give us. And next is just give some variation quantity, which is defined as follows, which is a little complicated. Consider the function belong one function which from the previous function space and satisfies such a condition. And to define this variation quantity, then one can show the later result, such that for family bounded non-negative Borel variable functions phi with compact subset in the domain B, then the following conclusion holds that the previous variation quantity, if it's greater than 1, then what we are looking for the exponential moment, which will be finite. In the opposite case, if the variation quantity is less than 1, then the exponential moment will be infinite. So this is the first calculation, and furthermore, it give a tail probability, which is also can be seen as the relativation principle that the rate function is similar to the uh, variation quantity. Next, still I will give the idea of the proof. The idea of the proof is that first we want to show that this, if the quantity greater than 1, the exponential moment will be finite, which can be solved by analyzing the asymptotic behavior of the moment generating function. Yeah, and to get the asymptotic behavior of the moment generating function, we need to use some tools which from the entropy and the relative entropy, such as KO divergence. This is like just the idea of the proof of for the first result. And for the second one, it will be in fact similar to the previous things. We'll try to use a theorem that to consider the logarithm Laplace transform and use the Gauss moment and to estimate the Green's function. So that's the idea of the proof. And then next, we'll introduce another work written by Professor Andre and this guy. They investigate the conditional moments of the Brownian intersection local time in 1 and 2 dimensions with the conditions at the end point that just consider the Brownian motion in 0, 1, where the end point is W1 tend to infinity. And why consider this problem is that the conditional behavior of self-intersection local time, which is inspired by study of the polymer models, the intersection energy between the monomers at a different part in a polymer molecules will affect the conformation. And this guy Flory proposed a method to estimate the size of a polymer, which is based on to calculate the interaction energy. And if apply Flory's method to this problem, you must substitute the interacting energy with the self-intersection local times, which of course a self-intersection which reflects the interaction, this behavior. So the question of the self-intersection local time and the size of a Brownian path, it's naturally motivated. Here first I show what this theorem says us that for any p which is greater than 0, and here's beta which is during 0, 1, here consider for two Brownian motion intersect p times the expectation of the local times under the conditions that W, the endpoint is equal to A, which has such a asymptotic result under the condition that the endpoint is tend to infinity. Also, I will just show the idea of the proof that first just consider the P to be an integer and rewrite the conditional expectation to be to be the following integral of delta functions, where the inside the process, which is equal to the following form, and then to do some representation based on the white noise. If we denote the white noise is W dot, that about is W, of course, is a Brownian motion, then we can get such a representation, which is where the function G0 is just indicate function, where the Q is a projection onto the orthonormal complement of the function G01. And to get the representation, the rest of the proof is just to try to do some representation later, and then to estimate to consider it the representation about the elements in the space, and to consider the grammar function of this projection, and then to estimate it. This is just the idea of the proof here. For someone is interested, maybe can check the paper. So next, we'll introduce another result, which is approved by Professor Chen and Song in 2024, which they give the small deviation for the mutual intersection local time of two independent one-dimensional Brownian motion. It's a small deviation, and here we can see the power is 2 divided by 3, which is different from the case that for one-dimensional Brownian motion intersected self-intersection, where under that case, if for one-dimensional motion, the power, of course, it's a classic result, but the power will be 2. Then I will also just give the idea of the proof that the first use some just well-known result, that the scanning property and the relation of the delta function. We rewrite the previous in fact, maybe I will emphasize it. The right part here is what we are looking for in the result. We see this equally distributed, and with this relation, the small deviation will deduce to establish the following bound. Here, in fact, here we used to consider a small deviation under the epsilon is 10 to 0, but under this representation, we will just go to investigate for this bound and consider that the t is 10 to infinity, which translated to other case. And to solve the previous to try to get the bound for this probability, it's very interesting. We'll begin with the lower bound. The idea of the proof of the lower bound is that I will write something here, like we consider here. Start with consider now is Brownian motion in the interval 0 to t. But here we want to divide it to be 2 interval from 0 to 1 and 1 to t. And we want to get that for one Brownian motion in 0 to t, which intersect another one in 0, in 1 to t, which is the intersect is empty. And also in this situation. And if these two conditions holds, what it will give us? The only intersections will only happens in this interval. Like only B01 will intersect B delta 01. So this translate our initial probability, which we can call it maybe the low intersection on the interval 0t with 2 power, which is greater if of course it will greater equal than the probability of no intersections on the interval 0 to t with 2 power. And with this relation, this is what we want to get, and then this is what we will go to investigate it. And for this probability, it will be easy to compute, so one can get the bound of it. This is greater equal than something. And then for the upper bound, we'll use some idea similar to this. We will try to also find something about the lower intersection, which is greater equal than the no intersection on some interval. But just the step, the idea will be a little different, but my step will be similar, but I didn't show it here. If someone is interested in it, may can check the reference. I will show it later. You can check it more detailedly. Okay, then the last result is from Professor Andrea and his co-author that they investigate the intersection local time involved to correlated Brownian motion on the plane, which formed a differing process in R4, which is associated to a divergence form object. They consider such a kind of Brownian motion. And then to establish the law of iterated logarithm for the intersection local time of such Brownian motion. Like I said before, that X is the differing process in R4, but express it as two correlated Brownian motion on the plane, which just think it to be two parameters, and denote the intersection local time of Z to be the following form. And then give the law of iterated logarithm of such a form that for two constant, 0 is less or equal than C1 and less or equal than C2. And the limit sub of this local times divided by a function where I think you guys knows what this means, is just a two logarithm. It belongs to the interval, so which means the limit sub is less or equal than C2 and greater or equal than C1. So I will just only also show the idea of the proof. To prove it, we also begin with the left part about the bigger constant C2. We want to prove such a probability is equal to 1. So of course the inner part, this random part is this limit sub is less or equal than C2. To prove this first, but it's not an easy step. We need to find C1 to prove it. The first step of the proof is to find C2, which will allow such a probability holds, that the probability of the intersection of time greater or equal than it. This will occur infinitely often, that this probability equal to 0. Since if seeing this infinitely often, someone may think about the Brio-Contelli lemma, which is says that if the sum of the probability is less than infinity, of course it's true. So to we want to prove this to find the C2 satisfies it. Of course, by the Breuil-Cantelli lemma, it will give us that the previous probability is equal to 1. So this is the proof for the upper bound. But for the lower bound, the idea will be also the same, that to prove that it is greater than C1. And also we'll follow like the step to try to consider to use some like the Breuil-Cantelli lemma, but I just say a little about the lower bound. It will use the idea the result, which is called the extended Breuil-Cantelli lemma, and the idea may be similar to this, but so I didn't show it here. And okay, that is the proof of it, and also this is the end of the result I want to show. Next here, this page is the reference for today's talk, and even I didn't mention it before, but it's related, or maybe of course it will relate to the talk of today's talk. If someone is interested, one can check this paper or even books for more detailed proof for something. Okay, then that's all for today. Thank you very much.
Okay, thank you very much for interesting survey. And maybe somebody have questions or comments, please.
I have a question about the last result about the asymptotics.
This one?
Yes. So, is there any hope to get some exact asymptotics?
Mm-hmm.
Of course, yes. But it is related to actually the same problem when we have any diffusion process which is written in the for which its generator is written in the divergence form. We have Nash estimations or Aronson estimations from above and below for transition density.
Yes.
And there are some papers where we can find the exact constants. They depend from the diffusion operators, from the generator. And if we have it, then we can continue, and then we can find these constants C1 and C2 explicitly. So they depend on the generator, and as precise we have estimation for densities, then as precise we have this constant. That's all what I can say for the moment. Still, under our approach, we will have a gap. So we
Yes, I
but
see.
okay.
But maybe we can find some variation or representation for universal C.
Oh, yes, you're right. It can be done exactly as for constants in Nash inequality.
Yes.
Okay. Mm. Some other questions, please. Alexei, you see this theorem of Mortos and Koenig about the Hausdorff dimension of sig points. I think it is closely related to your talk last week.
Yes, I saw that. I think it's interesting result, but I think it is a different type of Hausdorff.
Yes,
And a different type of set. So I don't know.
Because this is exactly what about Taylor's initial Taylor's work was also. My last comment previous week was related to such kind of results. Yeah.
Mm.
Okay. Okay. Some other comments or questions, please. If there are no concerns, thank you again for interesting survey. And maybe Georgi know who will be a next speaker.
Next speaker will be Mykola Vovchansky with a
Mhm.
talk about, as I understood, stochastic flows and the duals flows.
Okay. Okay, let's see. For today we finished our job. Thanks everybody and bye for the next week. Bye.
Okay,
Okay,
bye.
thank you.
Bye.
Thank you.
Bye.
Bye.